Just a quick test. Can anybody hear me out there? Well, my clock says it's 7:30, so I guess we should make a start. One thing I've found with these YouTube live sessions is it runs about 30 seconds behind what I'm saying, so you're seeing me 30 seconds in the past. So it's a little confusing when you get to questions and things, but I think we're going to do a Zoom after this, so I think Paul Cotton is going to set that up, hoping anyway. Anyway, right, let's get going with this. Just get myself sorted out. So this is about things that go bang in the night sky, which is largely going to be explosions, because normally I deal with things that take giga-years at a time, billion years, that sort of thing. So I thought it would be nice to talk about something that's a little more rapid than that happens in seconds or milliseconds for the most part, although we'll consider a few longer things as well. So let's start with what makes the biggest bang, or let's go through a few things and see what makes the biggest bang, because there's quite a few contenders. This tweet or this cartoon has been here since the first time I wrote this talk, which was about when this gentleman came into office, and it's still true now, I think, although there's probably different ways he's going to sort things out now. So that's still true. But before I go off into astronomy, I got this lovely story I found on the internet of Earth-based bangs, and perhaps one of the biggest bangs. So this came out of the nuclear testing at Los Alamos, where they used to dig big holes and sometimes drop large atomic bombs into them and detonate them to work out the physics behind them and that sort of thing. Anyway, in one case they had something called Operation Plum Bob, and they had Pascal A and Pascal B as part of that, which they drilled a big hole into the Earth, put a nuclear device in, and then detonated it. Anyway, Plum Bob A, the first one, went off, and that one went off apparently like a sort of a large firework, shot stuff up into the atmosphere and so on. So I guess that's what they expected would happen. But when they came to repeat it later, Plum Bob B, which was 1965, they decided instead to weld a metal sort of drain cover across the top to try and contain the explosion. And the gentleman, Dr. Brownlee, who was in charge, did a few calculations just before it went off and decided that maybe this welded fabrication would not actually withstand the blast of a nuclear weapon. And so they put a very high-speed cine camera to film it, and did indeed film it. But when it went off, true to form, this cast iron drain lid, which was about a ton in weight, I think, didn't stay welded to the top of the tube and instead shot up into the atmosphere. And they only managed to catch one frame of it leaving in this high-speed cine, which meant that it was going about 60 kilometers a second, which is quite considerable. And in fact, that is more than not only the escape velocity of the Earth, it's actually more than the escape velocity of the solar system. So they never found this retaining cap. It shot up into the atmosphere and disappeared from all time. Some thought that it actually melted as it went through the atmosphere, but other calculations show that it actually probably shot through the atmosphere unscathed and was probably the first thing to leave the solar system. So it beat Voyagers and Pioneers by some considerable time. So I thought I'd start with that bang. That's a man-made bang and probably one of the most interesting. It's also beat Sputnik 1 and Yuri Gagarin into space. I'm afraid there's quite a bit of theory in this one, so just stick with me. Try and make it as painless as possible. But let's start with how stars work. So you may well know this. The stars are big balls of gas, and they have two forces working on them. They have gravity pulling them all towards the centre, so everything is tried to be attracted towards the centre and would squash down to nothing if it could. But opposing that, you have pressure, both thermodynamic pressure and also the fact that you've got a big nuclear fire burning in the middle that eventually lights up and causes an outward pressure that's stopping the star from collapsing any further. So these two are in balance, and this is how the star spends most of its life in this sort of it's not completely unsteady. It's a fairly stable situation that it finds itself in, that the nuclear forces just balance the gravity because they come to a happy equivalence. But this leads to the problem that if one of these things should disappear, and it's not going to be gravity, that's the one true fixed thing, it's going to be the nuclear processes in the centre. If they should ever switch off, then suddenly you've got all this gravity that's still sitting around there trying to squash the star into nothing. And that's where these catastrophes happen, that something will collapse it down, and there's very few processes that can stop this from collapsing down when it starts. So the first state you can get into is a white dwarf. This is the end state of a star. When it's run out of nuclear processes, it just collapses down, and this is Sirius B, white dwarfs surrounding Sirius A, and the end state of indeed our sun. And these all live off somewhere on this this diagram down here as the white dwarfs. I don't know if you can see the cursor. So they all sit there down there. They're not very luminous because they're very, very small, about the size of an Earth, and they are quite hot because they've contracted down into this tiny ball the size of the Earth from something very large, the size of the Sun. So that they're quite hot but not very luminous because they don't have much area to shine from. So the first category I want to talk about is novas. So these are stars that erupt into brightness, but in a fairly steady way. But they set the scene for the ones that are going to come, which I'm going to spend most of the talk talking about, which is the supernovas. So novas are white dwarfs at the end of their life, sitting there with composed mostly of hydrogen and helium in the core, hydrogen on the outside. But at least one cause is if you have a red giant or something nearby, that can start to stream material from the outer winds of the red giant, which are very loosely held, and they will form a sort of blanket onto the white dwarf. As they're streaming across space and dropping onto the white dwarf, they pick up quite a lot of speed, so they hit the white dwarf with a certain amount of energy, which is converted into heat, and so gradually the white dwarf heats up and gets more and more of this hydrogen, and at some point you get this lighting up in a brief burst of fusion that goes around this outer core of very hot hydrogen and burns, and then pulses out into a ring of stuff that's shot out into space, and that's where you see the bright nova occur, and then it sort of all calms down after that, and it goes quiet again. But it could reoccur after it's blown off this one layer of stuff. It might well accrete some more and go through the process again. So you can go through it several times. And GK Persei is probably a good example of one of these that's blown off its outer layer, shot it out into space, and is now collapsed back into just a simple white dwarf again. So that's simple nova, but it, as I say, it does rather set the scenes for what's going to happen to some of these more extreme events. Now we'll go through a few more definitions and a few more processes. So I've said already that white dwarfs are the end state of small stars. They have an upper limit of 1.5 solar masses. Anything more than 1.5 solar masses cannot be a white dwarf. And we'll come on to exactly why that is shortly. But if they are more than this size, then they have a choice. If they're somewhere between 1.5 and 5 solar masses, and we're not really sure on the upper bound of this, it could be 3 solar masses, it could be 5 solar masses, somewhere around that, then it will collapse down into a neutron star, which I'll talk a little bit about briefly. And they are much smaller than a white dwarf, so 20 kilometers across, size of a big city, much smaller than a white dwarf, and be phenomenally difficult to find in the cosmos if they didn't sort of signal somehow. But a lot of neutron stars are also pulsars, so we can find them that way. Above at least 5 solar masses, and maybe above even less than that, it will collapse down to a black hole. And we don't know how small this will be because you can't look inside a black hole. But typically the event horizon, which is the point which you cross, you can't come back from, will be around 30 kilometers for one of these black holes. So what's going on in each of these? Well, in a regular star like the Sun, you've got regular matter. You've got atoms that are shown here as the nucleus in grey and the electron going around it in that's the orbit in red and the electron in green. So that's an atom, and these are quite compact within the centre of the Sun, about 0.1 kilograms, 100 grams per cubic centimetre. It's compressed down to in the Sun, in the core of the Sun. But they're just regular atoms at this stage. We'd recognise them as normal things, just a bit tightly packed. Other than that, they're just regular matter. When you go to the next stage, which is white dwarfs, then stuff is really very densely packed. They're squashed down until there is really not much room for anything to move around. It's no longer a sort of a gas. It's what's called degenerate matter at that point. And the atoms are now squashed as tightly as they can be, and slightly different physical laws come into play. And it's quite a different state of matter. So you can see there, it's 100,000 kilograms per cubic centimetre. If you think of a cubic centimetre as a sugar cube, 100,000 kilograms, 10,000 kilograms, can't read. That's pretty dense stuff. You know, that's not something you're not going to be able to lift a sugar cube of degenerate matter. And it has some very strange properties. If you heat it up, it doesn't really expand at all, which nearly everything else in the world does. So if you start to heat it very strongly, in the case of an explosion, it doesn't really respond very much. It just sits there, getting hotter and hotter. Another strange phenomenon for degenerate matter is if you add more matter to it, and this would be a white dwarf, so if you add more matter to a white dwarf, it shrinks in radius, it gets smaller as you add more matter to it. So very, very strange stuff. And it's held up really by these electrons. Electrons are they have certain quantum mechanical properties, but cutting to the chase is they all have a place to go, and there is like a pigeonhole for every electron in a white dwarf. And if you fill up all those pigeonholes, you can't squash it anymore. So it's like in regular matter in the sun, there's lots and lots of these pigeonholes that you could put electrons in. But by the time you get to degenerate matter, you've filled in all these holes, and there really isn't anywhere else for electrons to go. And it's this resistance against squashing that triggers this stopping in the degenerate matter state of a white dwarf. So this outward pressure that electrons really don't have anywhere else to go stops it from collapsing anymore. Now if you go to the next stage, which is the neutron star, this we've gone beyond the ability for electrons to push outwards and stop it collapsing any further. We've gone beyond this limit, and at this point everything collapses down until it's extremely dense. You're now collapsing down into the cores of atoms. So this bit here we can see is the nucleus of an atom. They're much bigger than this in real life. If this was a marble, this core of the atom, the nucleus, and you put it in the center point of a football pitch, the electron would be going around in the stands of the football pitch. So you can see an atom is mostly empty space. So by the time you get to this degenerate neutron star matter, you've got rid of all this. The electrons and protons and everything have collapsed down into just a very dense state. And here you can see it's 10 to the 14 kilograms per cubic centimetre. So basically a Mount Everest per cubic centimetre per sugar cube. So everything is really squashed down. And this is held up by neutron degeneracy pressure. In this case, we did have electrons filling up all the pigeonholes. Now the same thing happens with neutrons, but there's kind of a few more spaces for these to go in a sense. So they can withstand this pressure for a bit longer. But eventually they will have their limit, and once you exceed that, we don't know of anything further that can stop the collapse of a heavy object, so it collapses down into a black hole. And at least one more definition, when you're talking about supernovas, they often talk in terms of FOEs, which is a unit of supernova power. So it's 10 to the power 51 ergs, 10 to the 51 ergs. I don't know why they use ergs. We seem to use ergs quite a lot in astrophysics because they haven't switched over to joules. But if you are a little more modern, then it's 10 to the 44 joules, or the entire energy you could get out of demolishing 186 Earths. If you could convert all those 186 Earths into pure energy, that would be how explosive that would be. So let's start with some of these things. Let's have a look at them. Start with kilonova. So this is the merger of two neutron stars. When two neutron stars get very close together, they start to radiate a lot of energy in the form of gravitational waves. So they get closer and closer, and when they merge, they give off about 10 FOEs of energy. So this is 10 to the 45 joules, and this is what it would probably look like. I hope this comes out okay in this animation from, I think this is from NASA, showing them slowly getting towards each other and merging together. And this is something we've detected through gravitational wave astronomy. We've actually detected at least one of these events, and they give off a huge amount of energy. And because it's very rich in neutrons, it converts very conveniently into lots of heavy elements. So you can make lots of elements like gold and platinum and things like that very easily through this process. So I'm hoping that's coming out okay. Just look at my monitor. This was the gravitational wave gamma ray burst that was detected here, and you can see it doesn't come out very strongly from this picture taken by the Hubble, but it did come out quite reasonably in the gravitational wave detectors, which we got 3 of them focused on, so we could pinpoint it on the sky. Well, didn't actually pinpoint it, but it gave us a close enough place to look to work out where it was. And this was the paper with lots and lots of astronomers on that were acknowledged, and there's a few optical transients from this gravitational wave detected event. So as we'll see when we get to supernovas, the optical follow-up is often a day or two after the actual explosion. But in this case, this probably fabricated about 200 Earths worth of gold and 500 Earths worth of platinum. So it will be a rich place to go and harvest metals out there. Although it is, I think, about 1 billion light years away, something like that. So it's reasonably long round trip. So now on to supernovas, which are certainly the most exciting ones that I think we'll come to find. So these are the end states of stars that don't go off with a whimper like our sun, but they go off with a big explosion. And we've had quite a few through history, but sadly not any in the recent past. So here's a few notable supernovas. Get my teeth in. So the first one was 10,006. So these are named supernova SN 10,006 for the year. And this was the first one that was widely reported in history and was probably a magnitude of -7.5. So that was pretty stunning. You might well have been able to see that in the day. You would certainly have easily been able to see it in the night sky. That was about as bright as the brightest iridium flares. Far brighter than Venus or any of the ISS passes. So that was why it was widely reported and written up in records such as Chinese and even some of the Near East ones. Next one, Crab Nebula supernova, was 1054. So that was a -6, also very bright. We'll look at that in a bit. Then Tycho's supernova in 1572, and quickly followed by Kepler's supernova in 1604. These were both very bright, -4 and -3. So if you were looking at the night sky, you would have clearly have seen these as bright new stars. Then there's only two more recent ones that are close by. There's one in 1680, but that was a magnitude +5, so not very bright at all. In fact, only just visible to the naked eye. And that was in Cathay, very obscured by dust, which is why we didn't see very much of it. And then probably some of you might remember supernova 1987A in the Large Magellanic Cloud, +2.9. So not hugely bright, but for anybody looking in that area of the sky, you would, who was familiar with that area of sky would certainly have noticed it. So this is what they look like today. Supernova 1006, type 1A, and I'll come on to discuss the classifications of them. Crab Nebula one, type 2, 1054. And this is what the remnants of the Crab Nebula look at. We can still see it expanding even today, so we can wind the clock back, and this is how we know that this is basically when it occurred, from looking at the outflows from it. Then Tycho's supernova in 1578, 1572, type 1A again. Kepler's supernova in 1604, type 1A. And we'll come on to the other one later. So what are these type 1As and type 2 supernovas that I'm talking about? Well, this comes from the classification made by Minkowski and Fritzwicki back when they first started observing these things. So they basically said, here's a flow chart of what you do. If you see a supernova, then you go off and take its spectrum. And if you see hydrogen lines, then it's a type 2. If you don't see hydrogen lines, then it's a type 1 of some sort. But they quickly found out there were several types of type 1, and if there was if there was no helium lines in it, then it was a type 1c. If there were helium lines in it, it was a type 1b. And if instead it showed strong silicon lines in the spectrum, then it was a type 1a. So this is the classification they came up with. And it's not a very good classification now, given what we know, but it's still one we use. That's Fritzwicki there, sitting there. So he also had a type 3 and a type 4 and a type 5. but those have since been just those are now sort of subtypes of the ones we understand, the type 1s and type 2s. So now we understand a little more about supernovas and what do we think is going on. Well, they fall into two clear types. The type 1a are a detonation, so this is a star exploding, and the type, everything else basically, a type 1b, a 1c and a type 2, these are all core collapse. So this is a large star collapsing in on itself. This is where it stopped burning in the middle and it all just collapses under gravity. So let's start with type 1a, because these are perhaps a little easier to understand because they're very much like the nova. You've got, yet again, a white dwarf. It's come to the end of its life, just sitting there. Now, if it's something like the sun, it'll have made a little bit of carbon and oxygen in the centre, but around that will be helium and hydrogen. And then a companion star, such as a red dwarf, will swell up, and stuff will start falling off the red dwarf onto the white dwarf, red giant, onto the white dwarf, just like it did in the nova. It will fall onto there, and we'll get this blanket of stuff heating up as it falls on there and get very hot. And this time, though, when it lights up, because this is strongly degenerate matter, it just burns the whole way across. It burns right through the supernova because it doesn't really expand and explode like normal matter does. It just burns all the way across until it gets extremely hot, and then the fact that it does very, very weakly react to heat kicks in, and it does blow up at that stage. And this is a simulation done by, I think again, NASA, of what it probably looks like. So there it is, stealing it. Except I think they got this wrong, because they've got the remains of the white dwarf there, and I'm pretty sure in most cases there is not really much of a residue from one of these things. And if you want to see this modelled from internal processes, this is it going off internally, or at least a model of that. So starting perhaps from the centre, it trips over and starts to ignite. And one of the key things about these is they're all about 1.5 solar masses. So they're right on the boundary between where a white dwarf can survive and where it would tip over into a neutron star. And it used to be thought that it was actually the tipping over into the neutron star that triggered this. But the current thinking is that it's just instabilities that occur just as it's sort of beginning to get to this state that trigger it to fall over this thing and ignite. So there we are, it igniting into outer space, and they're very popular with astronomers because they nearly always go off at the same luminosity. We can use them to measure the universe. And there's one going off in a nearby galaxy. There is also a type 1ax, which is less powerful than a type 1a. These are very helium rich. They've probably lost all their hydrogen, and they are reasonably common but not as bright. And this is what a typical supernova looks like. The explosion is somewhere over here, so it's happened over here, and then it brightens up over the next few days until it gets to this peak, and then it starts to fade away. And the peak is actually caused by radioactive elements generated in the supernova, all decaying and giving off light. And so the peak is nickel-56, which is a fairly short-lived isotope, and cobalt-56 gives you the longer sort of fade of it. And if you run that over time, it looks like this. So you can see there on the left the supernova brightening and dimming, and on the right its light curve. So it takes a few days to a few weeks to a month or more to go through this cycle, slowly dipping down. And it's not, say, caused by the actual explosion, it's caused by the byproducts of the explosion. But they're not all exactly the same. this is a plot of lots of type 1a supernovas, and you can see there's some variation between them. But they've found, luckily, if you take the width of the curve, you can actually use that to calibrate things, and therefore get a curve that does give you a good indication of how luminous it is, so that you can again get back to measuring the size of the universe with them. So that's it for type 1As. Type 1Bs, 1Cs and type 2s, these are all core collapse. So something has happened in the centre of the star to switch it off basically, and the outer layers of the star have come collapsing in. So we remember back to this scenario that there's stuff happening in the centre to keep it burning, and as the star goes through its lifetime it gradually uses up its fuel. Here we are burning to carbon and oxygen, and bigger stars you can burn up to magnesium and up through silicon, finally to iron, and at that point you run out of material that you can fuse and the star just gives up at that point. This is what's happening in a very large star called onion burning, which is unfortunately no relation, it's just the way it looks, but you can be burning both all the way from silicon, oxygen, neon, carbon, helium and hydrogen, all in different layers at the same time. But you get progressively less and less from each of these stages, and then eventually just run out of stuff, and in fact the core of the star starts to soak up energy rather than produce it. At that point you get to this stage where you've got a very central core that suddenly collapses, and the rest of the star then follows in quick succession, dropping down. This is a very, very rapid reaction. It takes maybe a fraction of a second. It's that quick. The outer layers can rush in at very close to the speed of light. There's so much gravity there trying to pull everything in. So it's all over very, very quickly. And typically then there will be some sort of bounce back that, depending on exactly how big this is, it will bounce back and expand. Here's another animation, runs a little quicker. This is yet another of my animations, so not particularly good. But there we see at some point it just stalls. There is the force collapsing in and the wish to sort of explode out. And we're not still 100% what causes this sudden explosion. That stuff does drop down and it stalls for a while. Certainly in all the computer models it stalls at this point. And then something occurs, and we think it may be neutrinos that lift core up and cause it to explode outwards. Whatever it is, given our models aren't particularly good at predicting it, what we see in reality is that they do explode, so we do know it happens, and we just have to get a little better with the models. So I think the more recent models do actually get these things to explode, but for the longest time we couldn't get these stars to explode. They just dropped in and just sat there. So here we are with supernova 1987A, a Hubble photograph of it, and if this animation works, oops, I've overshot it there. Let me go back and see if I can trigger it. So this is several photographs taken over time of it. You can see there hopefully the time ticking away and the outer ring of material expanding out. It's not actually an expansion of material in this case, it's more the energetic radiation coming out and lighting up material that has been cast off in previous mini explosions, a bit like planetary nebula, that sort of thing. But in this case it's material ejected from the original star that is now being caught up by the radiation of the supernova and lighting up in these rings. So the other types, type 1b, this is yet again a core collapse, but in this case the star has shed its hydrogen envelope and it's just helium that's left there when it gets into the core collapse stage and gets to that stage and explodes. So we don't see much hydrogen in these ones. And a type 1c is really just much the same. The hydrogen shell has been shed, the helium shell has been shed, and we're left with just carbon and oxygen at the very centre to get caught up in the explosion. So that's why we don't see these hydrogen and helium lines in this explosion. The type 2, there are a couple of variants on this one. So when they do collapse, they go off with different views. So this is sort of the simplest. It's called linear, although how you draw a straight line through any of that curve, I don't know. But this is called a linear supernova type 2L. And you can see this rises to a peak and then collapses down. So the explosion is all the way over here. This is where we see the peak of the brightness, and then it fades slowly down this slope, much like a type 1A in this case. And we think this is caused by a star exploding and casting off a very thin layer of material. So this is where all those nickel and silicon short-lived isotopes, radioactive isotopes, are giving off lots of bright illumination. And they're all sort of caught up in this shell and giving off the light. So that just sort of goes through fairly straightforwardly. The next type is a type 2P, and this is because it has a plateau in its curve. So much like the previous one, we have an explosion, a peak, and then a plateau where it seems to stay at the same brightness for a while before eventually fading. And this one looks a bit like the previous one. Oops, I've gone too fast. Except the ring of material here is much thicker. So you have this ring of material with these short-lived radioactive isotopes all giving off this bright light, but it gets trapped within this shell and it sort of bounces around and sort of rattles around for a bit before coming out, which gives you this plateau of time while the light is all trying to get out of this shell of material. Keeps it at its sort of brightness for a while. Then there are a couple of other obscure ones which are really of only interest to supernova hunters. Type 2N has narrow hydrogen line. Type 2B looks like a type 1B after a while. But if you plot them all on the graph, you can see they're all slightly different. The type 1A in black gets perhaps the brightest. See the type 2B, the type 2P, the plateau one in blue, the long plateau. And then various other types giving all sorts of different curves. So if you watch them for long enough, you can sort of work out what type they are anyway, but spectroscopy gives you the best. Then there are things called hypernovas. These are extremely energetic explosions caused by very large stars that are exploding. And in this, the shell explodes but then falls back and then creates this large jet of material that shoots out of them. So that's the sort of hypernova event, and it's a bit like a pulsar in that you get a very rapid rotation of beams that are shooting out of the resulting core collapse. And you'd think that would be it, but there are different reasons to why a star's core will collapse. In the end, it's running out of energy of some sort, but there are various ways you can run out of energy. And the first type is called electron capture. And this is quite a recognized process. So this is an electron going around the nucleus of an atom. And usually they sit around doing that all the time. But occasionally the electron can get absorbed into the nucleus like this. This is a process we see on Earth. There are certain radioactive elements that do this anyway. It's called K-capture. Quite often. So the electron just gets absorbed into the nucleus and the electron disappears. You do get a neutrino given off, which sort of balances the books. But anyway, if you get a star of somewhere between 8 to 10 solar masses, so this is the smallest star that can go supernova, you have a very degenerate core made up of oxygen, neon and magnesium sitting there burning. Well, that's not burning. The shell of material around it is burning, but the conditions are very favourable for this to undergo electron capture. The magnesium can start capturing electrons. Now, if you think back to degenerate material, I said degenerate material is held up by all electrons being in their little pigeonhole, all knowing where they should be, all contributing to holding up this degenerate core. If this magnesium starts stealing these electrons, suddenly you're emptying the pigeonholes and you get rid of this force that's holding up the centre of the star. So that quickly turns this from a degenerate core to something that can't withstand the pressure, and it collapses down quickly into, well, basically a neutron star at this point. So the core collapses into a neutron star and the rest of the material just falls in after it. So this will give you a faint type 2 plateau supernova and results in a neutron star as the result. The next type is for a whole range of solar masses, about 10 solar masses to 140 solar masses. And in this one, you burn through all the elements and you end up with an iron core that doesn't do any further burning. This is also very degenerate because it's under extreme pressure. And in this case, this one just tips over this Chandrasekhar limit and goes from basically a white dwarf, is what it would be if it weren't in the middle of a star, to a neutron star. So it goes from something the size of the Earth to something the size of Birmingham or something like that, again in a fraction of a second, and the rest of the star follows through, collapsing in onto it, giving you the supernova. And this gives you all sorts of different ones, depending on exactly how much stuff is jettisoned in the explosion or exactly how big it was. You end up with either a neutron star or a black hole, and you get all sorts of different supernovas. It really depends on the life of the star that's gone on before this. So that covers the majority of stars, certainly in our galaxy, because 140 solar masses is a very big star. I mean, Rigel is 15 solar masses, something like that, and that's one of the bigger ones around. So 140 solar masses is a huge star. But that doesn't stop the theorists. The next one up in the range 140 to 250 solar masses is a pair instability supernova. And what causes this? Well, this is basically E equals mc squared. This is burning so fiercely you're getting extreme amounts of gamma radiation given off in the core. It's burning so violently that the gamma ray photons given off now have enough energy that they can actually create matter. So by E equals mc squared, they have enough E to create a certain type of M, and in this case it's pairs of particles, so typical electron and positrons. So this is what they start to do at this point. There is enough energy around to create these pairs of particles, so the energy goes into creating particles and not into holding up the sun. So up till now it's been this intense radiation that's been pushing out against the force of gravity holding up the star, but now it's suddenly switched and said, no, instead of holding up the star, I'm going to make lots of new particles of electrons and protons. And then again, suddenly the outward pressure is taken away and the star collapses. And drops down because the pair production just soaks up all the energy that was being used. So pair instability. These are going to be very, very rare because any star greater than 140 solar masses is just very, very rare. There's only a couple of those I can think of in the Milky Way or environments around there. In fact, in the Large Magellanic Cloud, I think there's a 300 solar mass star. So one of those going off might well cause this. So we think 2006 GY was a supernova of this form, and you can see how that was plotted against more typical supernovas. As I said, supernovas are labelled by their date, so 2006, and then I think the first letter is the month or the half month it occurs in, so I think A is the first part of January and B is the second part, and then you stick other letters on to distinguish them. So you could work out, I guess that's going to be sort of April time, and the Wythe supernova they saw in April in 2006. So back in 1987A, there were very few supernovas seen because we didn't really have the telescopes to see them much beyond our very nearby galaxies. Nowadays we're seeing them all the time because we have that much better telescopes, CCDs and automated software to find them. So a pair instability results, probably a type 2P and a gamma ray burst of the long form, and it probably doesn't result in anything. The explosion takes the whole star with it and leaves nothing behind it. Now the theorists can think even harder, and above 250 solar masses, which is beyond the pair instability, at this point the energy is so violent in the centre that it actually turns on itself, and the iron core that was being formed, the energy starts to be soaked up by the iron core as it absorbs the energy and fragments it into helium and other basic elements. So the energy is just turned on itself and starts consuming the core of the star itself. And yet again, another one. Snow flash, probably a gamma ray burst, and a very large black hole would occur from these, but I don't know that we've ever seen one of these. Supernovas are affected by their conditions. So there's a nice plot. I think this is from Wikipedia or a paper on supernovas, shows you all the sorts of supernova. So here we are, solar masses. So this is about where our sun is. This is all white dwarfs over here. These are the type 2P, the very weak ones, and then you have the different types of bigger ones as you get up in mass. But they're also affected by how much impurities are in the star. So our sun is a type 1 star, so that has quite a lot of impurities, so that also affects how things get there. But let's briefly consider a few other big explosions that might happen. Black hole collisions, we've seen a couple of these in the gravitational wave detectors, so these are certainly extreme events, but probably not as exciting as a supernova, at least to look at. Two black holes that spiral around each other, and as they get particularly close they give off a lot of gravitational waves. In fact, the two initially detected, they gave off 3 solar masses worth of energy in their explosion. So that is a lot of energy. That is more energy than all the stars burning at once for that fraction of a second. So we're doing pretty well at detecting these. I'm sure we've got more than 6 by now. But these 5,300 FOEs, so if a typical supernova is between 10 and 1 FOEs, you can see these are enormously explosive events. We can take it a step forward and have supermassive black holes. So they are at the centre of galaxies. We know galaxies collide from time to time, so we would have supermassive black holes colliding. And these happen at a fairly short timescale for these things, because they are such heavy things. They are responsible for what's called dynamical friction. They drag stars into their wake as they move around, which slows them down. So they spiral down into the centre of the galaxy fairly quickly. So we don't know exactly what one of these would look like, and we can't detect them in gravitational wave detectors because they're out of the range of those. We need something like the LISA probe to detect those. Next biggest thing is an active galactic nucleus. These are very long-term events, supermassive black holes giving off quasar-like material. A lot of power, 10 to the 9 FOEs, but over 1 billion years or so, so not quite as exciting. And then just to wrap up, the biggest bang of all is the Big Bang. I thought I'd make a quick canter through this to tell you what's happening with that. So it's basically generated everything we know in the universe, so it's the source of all energy. And the furthest we can go back is 10 to the minus 41 of a second, a time so small that we don't have time 10 to the minus 43 actually. That's the Planck interval, the smallest time measurable. And it wasn't an explosion in space, it was an explosion of space, and it's continuing today. And if you could get your head around that, you're doing a lot better than I have. So at these very early times, we think all the forces that we know about, the four forces we know about, were all combined. That's the theory of everything down here. We are just about getting into this region with our particle colliders. So we've combined electromagnetic and weak forces. And the theory is that all these forces are actually just variations of the same force, but at different energy scales. They at lower energies they separate into the four forces. We know at higher energies they just all look very much the same. Between 10 to the minus 32 and 10 to the minus 36 of a second, again a very, very, very tiny period, we had inflation, in which the universe, as it was, grew by an enormous amount, at just a staggering time, 10 to the 50 times increase. So that's this many times it got bigger in such a short time that we don't even have a unit of time for it. But we think this happened for at least 3 or 4 good reasons, or at least the evidence is around for 3 or 4. And it was the fourth of these that Knuth was looking at, which was magnetic monopoles, which are individual magnetic monopoles. So a pure north or a pure south. We don't see them normally. A magnet has both a north and south pole. So Guth was looking at a way of getting rid of these and came up with this Big Bang inflation. But at a stroke, it solved 3 other problems that were also a problem. So the first one is the horizon problem, which is if you look to the horizon from the Earth as far as you can, it's 2.73 Kelvin. That's the cosmic microwave background. But likewise, if you look in exactly the opposite direction, it's also 2.73 Kelvin. So light, the fastest thing we know, has been travelling from 13.8 billion years and got to the Earth, and it would take another 13.8 billion years to get to the other horizon. So these two things are not, there is no way of communication between these two places, yet they are exactly the same temperature. So this is solved very neatly by the fact that if the universe expanded dramatically fast at this inflation, these 2 points would have been in contact before that, and they are now separated apart. This does slightly boggle the mind, but Einstein does allow space to expand faster than the speed of light. He just doesn't let anybody know about it because you can't communicate faster than them. There's also the flatness problem, which is that the universe appears to be flat, which is not a problem. We used to think it might be curved, so if you went on in the same direction forever and ever, you would eventually end up where you started. Much like walking around the Earth, you'd eventually end up where you started. Although there are other geometries, but our best measurement so far is it's flat. The trouble with that is it's a very knife edge position for the universe to be on. It has to be almost perfectly balanced to be flat. A slight teeter in one direction or the other and it will go somewhere else. But a very expanded universe could actually be curved and just stretched out very much. So our geometries we see, they could look up any of these, but it's the top left one of triangles that add up to 180 we see across the universe. Then finally there's a structure problem. If it was a uniform universe that just expanded, nothing would happen because it would be so uniform, nothing would clump together and form, but we do know that happened, and we think it's quantum foam that was stretched big by this big expansion. So inflation solves all this, particularly by expanding so large that something that was curved now looks almost flat from where we appear. The next big thing in the Big Bang was just a desert of nothing much happening from all these times. Then we have the quark period, where quarks are just rattling around before they start to form neutrons and protons. Then we have the phase transition where quarks start to form protons and particles we understand. At this point we should have seen neutrinos decoupling, which I'm going to skate over. Then we have a lepton era where we have protons and antiprotons sort of exploding and giving off radiation, matter and antimatter meeting, giving off radiation, but the radiation is so high it yet again forms more things. Then about 3 minutes we get nuclear synthesis, which is where the whole universe looks like a star and it can start to build up elements. But it only gets 17 minutes or so at this point. Then we get the photon era where the universe is so dense and so hot that even light can't get very far before it's blocked by free electrons. So it's a very fuzzy universe at this point. But then 380,000 years after that, basically the universe clears, and this is where we see the cosmic microwave background. And we have the dark ages where nothing happens because everything is too dark and nothing has happened yet. And then we get to where we start to see now stars and galaxies form, probably about 4 million years after the Big Bang, sorry. And at that point, stars and galaxies can start to form. Then we get a period probably only interested to cosmologists, which is reionization, where the universe starts to reionize again. And then we get to today. So just recapping, the biggest bang is the big one that caused all of us. If you want to go on pure power though, active galactic nuclei are some of the strongest. If you want shorter events, black hole collisions are extremely energetic, but really not very interesting to see, even if you're close by. So for my money, supernovas are the most interesting, and we are well overdue for a supernova. We haven't had one since Kepler's time, so we're really overdue one. And looking at other galaxies, they happen around every 50 to 100 years in every other galaxy, so we need one nearby. We might well have had one over the other side of the galaxy that we can't see, but I'm hoping that we get something nearby. So thank you very much for listening, and I think at this point Paul Cotton, we were going to suggest a Zoom conference. Was that still the plan? I don't know, you're all 30 seconds behind me in the future. So we'll see where we get to that. Meanwhile, you can type questions in the chat if you have something. If we're going to do it on Zoom, we're going to need some sort of ID. Meanwhile, thank you very much for listening, and I hope you heard all that, because the last time I tried this I forgot to switch on my microphone for about the first 2 minutes, so that was rather dull. I'm glad. I think some people have heard it at the very least, so that was good. See if there's any mention of Zoom discussions, or whether we're going to... Oh my goodness, Kathy Elizabeth, you're watching this talk, are you, with your aunt? I don't know what she'll make of this one. This was a bit technical, perhaps. Oh, jolly good. Paul Money saying it came over loud and clear. That's always good to hear. I could actually hear you saying that, Paul. No, I didn't just see the typing. Right, I think this point I'll probably finish this, and then if Paul Cotton has got a Zoom worked out, we'll go with that. But I'll end this stream for now, and we'll see where we end up with that. Thanks everybody for coming anyway.